As mentioned earlier, reactions generally do not go to completion, and so we say that you generally don't expect to get your theoretical yield. Your actual yield will typically be less than your theoretical yield. So what are some of the reasons why our actual yield is going to be less than 100%? Well, one reason is a reaction may not actually go to completion. So it's possible your limiting reactant is not actually used up. In fact, that's pretty much the case most of the time. Also, you could lose product, any product you make in the recovery process. So that would also lessen your percent yield. Now, if you're in the business of making something by running a chemical reactions and you make something so you can sell it, make money, then generally what you want to do is you want your reaction to have as close a yield to 100% as possible. You want to improve your yield, and a common strategy for doing that would be to use a very large excess of one reactant. You'll learn more why that's the case when you get to a lesson on chemical equilibrium and Le Chatelier's principle. But the idea is if you use a very large excess of one reactant, then you tend to get a higher percent yield. And since if you're in the business of making money, then you probably want to use the reactant that's cheaper. Okay, use a large excess of the cheaper reactant. So here's a problem involving percent yield. Consider this reaction. 2A plus B yields C. Suppose you have 0.3 moles of A and 0.2 moles of B. You allow them to react, and you only got 0.12 moles of C. What's your percent yield? Well, first thing you need to do is figure out your limiting reactant, right? So let's see. What would be the extent of reaction if A is limiting? You're going to say 0.300, okay, would be equal to, all that would be gone, so that's going to be equal to 2x, right there. So our extent of reaction is going to be 0.300 divided by the coefficient of 2, which is going to be 0.150 moles, okay. If B is a limiting reactant, then you're going to use up the 0.200 moles of B, so that's going to be equal to 1x. So our extent of reaction is going to be amount of B, 0.2 moles, divided by coefficient of B, which is 1, which is going to be 0.200 moles. Okay? So the one that gives you, the reactant that gives you the smaller extent of reaction is your limiting reactant. 0.15 is less than 0.2. So this is your valid assumption. Okay, this is the incorrect assumption. So your limiting reactant is A, so we can predict our theoretical yield based on A. Would be equal to, we're making C, right? It's just going to be equal to C, which is going to be X, which is going to be the X when A is consumed, which is 0.150 moles. Okay, C. So your percent yield is your actual yield. Your actual yield is only 0.12 moles of C. Divided by the theoretical yield of 0.15 moles of C multiplied by 100%. So 12 out of 15, that should be about 80%. 0.12 divided by 0.15, 0.8 times 100, that is 80% yield. Okay? All right. So here's another way you could have done it. If you want to do it the traditional way, you can say, let's see. Here's a traditional way of doing it. If A is a limiting reactant, you would say 0.300 moles of A. How much C can you get? You can say times 1 mole of C for 2 moles of A. That gives you a theoretical yield of 0.15 moles of C. Okay? Just 150 moles of C, as we got earlier. Now, if B is the limiting reactant, Then you say 0.200 moles of B would be used up, right? That's given, 0.200 moles of B, times the C to B ratio is 1:1, times 1 mole of C for 1 mole of B. Moles B cancels, and that gives you 0.200 moles of B, of C, I'm sorry. Well, by the time you make the 0.15 moles of C, A will be gone, so you cannot make 0.2 moles of C. So this assumption that B is a limiting reactant is the wrong assumption. In other words, you can go ahead and figure out the theoretical yield based on those two assumptions. The assumption that gives you a smaller value for the theoretical yield, that has to be the correct assumption.